Welcome, grade 10 mindsetters. Finally, the time has arrived. It's Monday and it's time for maths. Guys, I hope you're tuning in. This is Dina, and Dina will be taking our lesson today. And before we start, I want to give a big thank you to Liberty for making this awesome show possible. Dina, what are we chatting about today?
Indeed, we are looking at number patterns in grade 10. We've covered some of it in grade 9 already, but I think this is getting into the real mechanism of number patterns as we need to develop through to grade 12. So number patterns, here we are.
Yeah, number patterns, grade 12s, grade 11s, join in too. I mean, there's nothing wrong with learning more and learning extra.
Absolutely.
What we're going to do is we're going to take a short break. Guys, get those questions in. facebook.com/learnextra. Also, our Twitter handle is @learnextra, so go chatting. Let us know if there's anything you're struggling with, and I'll ask Dean along the way. See you now after the break. Hi guys, and welcome back. I'm excited for an awesome lesson. I think today we're going to be learning lots and lots. Guys, I hope you had a fab weekend and you're ready for a week of hard work, but a little bit of fun too. And what's more fun than sitting in front of the TV and watching us and learning more and learning extra? So get all of those questions that you're wondering about in so we can get them answered and help you out. But without further ado, let's go straight to Dina.
Hi everyone. This afternoon we'll be looking at what number patterns are all about, and I think you have seen these since you were possibly in grade 1 when you started counting in ones. So a 1, 2, 3, 4 is a number pattern, and I'd like to look at what the terminology, what the vocabulary, what the notation is around number patterns, and then we're going to work through some examples together before you start bringing in your questions. So let's have a look at that sequence of numbers that you worked with in grade 1. If we looked at 1, 2, 3, 4, let's just see what the computer's doing.
Just click that pen. There you go.
Okay, we've got 1, 2, 3, and then we'll usually indicate the next set of numbers just by a series of dots. And we now look at each part of that sequence or that pattern. We use the word sequence or pattern interchangeably to denote what each of those terms may mean. So the first term will be called T1. The second term will be called T2. And the third term will be called T3. So T standing for term, and then this little subscript will always refer to that little term in that sequence. So if I was talking about T10, then I'd like to know what the 10th term in the sequence would be, and so forth. So if we went all the way to Tn, we would have n representing one of the terms in that sequence. Now Tn is also called the general term. Okay, this computer, it's doing strange things.
You know what? Sometimes it's just like your hands try and just point and write. But what I want to say in the meantime, guys, while Dina gives the little board a bit of a test, I know that a lot of our events have actually disappeared on the Facebook wall, but we have redone the events. So guys, please ask your questions in the grade 10 maths wall. And get your questions in. So if there's anything that you're not understanding, let me know on the page. My name's Indiana and I'm your page community manager, and what I do is I get the teachers to answer the questions that you so badly want to ask. Dina, how's it going there?
Okay, maybe I've conquered this thing. I think it's looking better. You've got to fall in love with this pen before it starts working. Right, so Tn is that general term, and each of the subscripts refers to that term in the sequence. Now, we'd like to do a little bit more on these and to say that this sequence, what do we observe? What is its nature? What does it look like? It goes up in ones, and we've got a special maths name for that goes up in ones. We would talk about the difference between these two. So it would be T2 minus T1 gives us the going up in ones. And this will then be called just a little d to indicate that it's the difference between those two terms. Now, this would be a general example of what number patterns would look at. I'd like to look at another. How would we go on to the next page? Just click on here.
Yeah.
There you go.
There you go.
Okay. Another sequence that you're very familiar with, and those would be the even numbers. And let's see whether we could come up with a general term for the even numbers. So even numbers would be 2, 4, 6,
Gremlins.
6. Every time I do a semicolon, it will do something else. But anyway, let's try. 8.
I think it's because of your elbow. Careful, your elbow.
So again, we would start with T1, and that one would be T2, T3, and T4. So those are my first 4 even numbers. And
Now let's come back to another page.
okay, and yeah, let's look at what would the nth term be. If I had to ask you to find the nth term, in other words, any term in that sequence, what would the formula for that nth term be? Now in grade 10, we only deal with what we look at in terms of the numbers, and they're not exhibiting any other patterns except that we're going to add or subtract something from those patterns. So some of you may have come across the Fibonacci sequence, or you may have come across an exponential sequence, or many other sequences that there might exist. But in the grade 10 syllabus, we're only going to focus on those where there's a common difference. In other words, you're adding the same thing all the time. So we did the sequence of 1s. Even numbers would be a sequence of 2. Odd numbers would be a sequence of 2s as well. And then next year, we'll look at what the quadratic pattern would look like. And then finally, in grade 12, you look at what, when you multiply by the same value, what those sequences would look like, and the wonderful patterns that they themselves create. So the one question we always want to ask ourselves is there a formulae that would give us that nth term? So the 1,000th term, the 10,000th term, how could we calculate that term? And if we were told what the value of a term is further down that sequence, would we be able to tell what value that term is? So I've given you a little bit of the terminology and a little bit of the theory behind it. I think we should go to a break, and after that we'll look at the evens and odds in terms of actually finding out the value of those terms in the sequence. So Indy, back to you.
Thank you so much. Okay guys, get those questions in. Let us know if there's anything you're struggling with, even if it's just to say hi to all the mindsetters and the team mindset, that's fine too. So let's go to a break, stay tuned, don't leave, see you now. Welcome back guys, I hope you're enjoying the lesson so far. It's amazing how 15 minutes goes by so fast. Dina's going to be going over an example for us, so let's get straight to it and get those questions in. Take it away, Dina.
Thank you. We're looking at the even numbers as an example of how to work with linear patterns. So let's look at how to create the general term of the even numbers. What would all even numbers look like? On the board I've got the 2, 4, 6, 8 sequence with the general term, and anyone that asks you for a general term, any generalization that gets done in mathematics, all you are saying is you're creating a formulae that would work for all cases. That's what's called as a general term. And so all cases in any sequence would be the Tn sequence. So we're looking for the nth term, and that's what we call it, the nth term of a sequence. So that would be my nth term. Okay, and the sequence is called linear because I am going to add, let's look at that, I'm going to add 2 to 2 to get 4, I'm going to add 2 to 4 to get 6, I'm going to add 2 to 6 to get 8, and so my pattern is the same. There's a constant 2 that's being added all the time. Now, before we jump into what this nth term is for the evens, I want to look at, let's go on to another page, and just write that again, but I'm going to split them up a little bit just so I can show you 6, etc. We only need the first 3. Okay, where the first one, because it's linear, any linear expression will always have a coefficient plus a constant. So my nth term will be a coefficient of n plus b, where n is to the power of 1. And that's why it's called linear, because remember from grade 9 where you did the straight line, your straight line equation was y equals mx plus c, where x was to the power of 1. And so an expression that involves a power of 1 will be drawn graphically as a straight line, and that's where the linear equation comes from. So this one is a similar equation where there's a coefficient, there's n that stands for the n in the term, and then there's a constant b. So that will be the general term for everyone. So if this is T1, and this is T2, and this is T3, then this term 1 over here, if we take that general term as an plus 1, then T1 will look as follows. N, the first term, is equal to a, n, standing for 1, plus b. And so your T1 will simply be a plus b. If we look at T2, and we now look at that T2 there, T2 is a, remember n stands for the term that I'm looking at, n is 2 and plus b. So now I get T2 as 2a plus b. In other words, I have formulated a general T1, a general T2. In all cases, my T1 will always be a plus b, and T2 will always be 2a plus b. So if I had to take the difference between T2, T1, I know that for my example it's 2, but let's see what that 2 would equal to in terms of the general term. It would be 2a be 2a plus b, and then I'm going to take away what T1 is, so I'm going to take away a and I'm going to take away b. So I'm left with 2a minus a is a, and b minus b is 0. So this T2 minus T1 is just equal to a. So if we carry on, we have our a value is always going to be the difference between T2 and T1. So remember when we said the general term, Tn equals an plus b, we now are saying that to get your coefficient of that general term, all you need to go and do is take the difference between T2 and T1, which in the even numbers, the difference between 2 and 4 is just 2. So therefore, for even numbers, my Tn is going to equal 2n plus b. So I'm getting rid of the a, I'm getting rid of the b. What will the value of that constant be equal to? Well, that's easy. We're going to take the first term, remember it was 2, 4, 6, etc. Tn's value for T1 is 2, so that's equal to 2 times 1 plus b. So my b, if I solve the equation, would be 2 minus 2 is 0. So my b is 0. So my even numbers then are going to be Tn, all even numbers, are of this form, 2n. So any description of even numbers would have a description, an algebraic description of 2n, and so that pattern can be represented algebraically as 2n. If the even numbers have a pattern, what do you think the odd numbers would look like? What would they be expressed as if I wanted to get the next even number, or the next odd number? Well, how far apart is an odd from an even? 1 or negative 1. It's on either side of that even number. So if I had to add or let's go on there. Actually, can go on there. Can I go down?
Yeah, I think you can. Just give it a bit of a push down. Maybe it's best to start in
there we go.
extend
There we
page. There you go.
There you go. Okay. Oh, wonderful. I found a little trick. Right, my odd numbers, since they are on either side of 2n, could be represented as my general term, either 2n plus 1, 1 more than the even, or 2n minus 1 on the left side of the even number. And if we were to look at what their general term would be, let's look at a sequence of odds. And let's look at the odds starting off from 3, 5, 7, etc. We learned that to get Tn, the A value is always T2 minus T1, which in this case, it's again 5 minus 3 is 2. So our general term Tn is going to be An plus B. And a number of you are going to be asking, is it always An plus B? Yes, because the linear always has a coefficient and a constant. Coefficient is A and the constant is B. So yes, it's always going to be that. And for our odd numbers, it's going to be 2n plus B. How do we find B? We take and we substitute in that first value, that first term.
Welcome back, guys, and thank you so much for sending in some questions. And you know what? They really are good questions. And this is something I really have to stress, guys, is that there's no such thing as a stupid question. Something that you're wondering, there's probably about 20 other people out there that are wondering the same thing. Okay, so I'm going to read this question to Dina, and Dina's going to work through it, and then we're even going to post a challenge for you guys afterwards that you can work through during the break. Dina, are you ready for me to read?
I'm ready.
I'm going to read out the question. Okay.
I'm ready.
So we've got two mindsetters. We have Alicia, who's asked a question, as well as Sontaga, and they're actually quite similar. Alicia said, Dina lost me at A. And then I was a bit lost by the comment, but then thank goodness Sontaga actually made it clearer for me. He said, hi there, kindly ask for you guys to explain what the Tn, the A, and the B mean. Thanks. And I'm sure, guys, watch for Dina's answer. She's about to take it away.
Right, that's an excellent question. We have to know the rules of the game before we can play it. So we really must know what each one of those variables mean or represent, because we're going to keep using them in grade 11 and in grade 12. So let's really get a handle on what the value represents and what it signifies and what we can do with it and how we can play with it. Okay, so let's go back to those even numbers. I'm just going to get another page. There we go. Right. Tn is any term. So T stands for the term in the pattern. Okay, so if I'm creating a pattern and you are going to give me a series of numbers, then for me to tell you where I am in that sequence, I'm going to call out or identify that specific term. So T is that thing that identifies the term in the pattern. And when I say N stands for any. Now, it could be N, it could be K, it could be A, it doesn't really matter, but mathematicians have conventionally given it the N as the nth term. So is any term, and we also refer to it as the nth term. So if I say to you T1, okay, let's just do that nicely, T1, then what exactly are you referring to? It's like calling a person by name. We are calling that term by name. So T1 refers to the first term because there's a 1 as a subscript. Okay? T2 is calling the second term by name. 2 referring to that second term in that pattern. So it's a unique position. Whereas Tn refers to anyone. You don't know which one you're going to refer to or going to call, so you say the nth term. Okay? So T3 refers to which term in the sequence? The third one. So you know exactly where to go. You're not going to the first or the second, you're going to the third one. Does that make it clearer, Indy?
Yes, I'm sure it does.
Good.
Thank you, Dina.
Okay. So Tn is the name of the terms or the labels that we give the term. And the A N plus B refers to the expression, there's an algebraic expression that you're going to be able to derive for every single pattern that is linear. And I just need to get the computer to listen to me. Equals A N plus B. So that would be a linear pattern. What do I mean by linear? It means that A is going to represent a coefficient, and B is going to be a constant, and N is to the power of 1. So remember the nth term, N stands for the name of the term. So if N is 1, the first term. If N is 2, the second term. If N is 3, the third term. So N represents any term in the sequence. But when N is being multiplied by something, it's not always multiplied by 1. It could be multiplied by 2 or 3 or negative 2 or negative 3. So this value over here is just a value that N is multiplied by. So it stands for the coefficient of N. So whenever you find a linear sequence, you're not just going to have N there. You're going to have something multiplied by N. And that something we represent by A. And then the B we represent as a constant. So it will be a constant term. So a linear function, the maximum that this linear function can be is always to have firstly a coefficient and secondly a constant. It sometimes might have be a 0, but this is the greatest expression that a linear can have. Now, I'd like to show you what a quadratic looks like so you can see the difference. Let's just extend this page. So let's just go down here. So if we were looking at a quadratic pattern, then we would have Tn equals an squared plus bn plus c. So anything that's quadratic, in other words, to the power of 2, will have one of the highest power is 2, but then it will have a term with an n, and then it will have a constant. And you'll certainly deal with these next year. If it was cubic, then the highest power would be 3, then you'd have a square and a linear and a constant. So it's the greatest way that an expression can be expressed if it is linear. Okay, so it's a convention, it's a mathematical convention. So you wanted to know what A was, and you wanted to know what B was. A is the coefficient of n, and B is a constant term. How we get those, we will have to look at another example. Shall we look at another example?
Yes, let us. Yes.
So let's...
What we could even do, we also want to give the learners a bit of a test during the break. So if you've got one of those,
okay, we can do that.
We've got a break in about 5 minutes' time. So guys, I hope you guys are feeling sharp and ready for a challenge.
Okay. All right, so if you are asked to find the nth term, you'd always start with, it looks like this. That's what it looks like. Your job is to go and find what A is and find out what B is, okay, in this whole process of finding that linear pattern. And if we look at the pattern 5, 8, 11, etc., then we can see that we're going up in threes. But if you wanted to find out what is a term down here, let's say the 50th term, okay, what would the 50th term look like? Are you going to sit 11 plus 3 plus 3 plus 3 until you get to 50? Well, that would be pretty boring, and that's not what mathematicians do. Mathematicians want to find the quickest route to find the 50th term. So we'd like to say, if I had a formula of finding all these terms, then I would just have to plug into the formula, and voila, we'd have the 50th term out. So we don't really want to sit there and plus 3 for all these terms and then find the 50th. You can by all means do that, but you're actually giving yourself a little bit of punishment. So let's find the most elegant way of actually determining what that formula is without adding threes. And the A that we found is always going to equal to the T2 minus T1, just recapping from earlier. And that, in this case, is 8 minus 5 is equal to 3. So again, I repeat, will A always be T2 minus T1? If it's linear, in other words, if you're adding the same thing over and over again, then yes, A will always be 3. So Tn will now at this stage be 3n plus B. So our job is to find A and to find B as well. How are we going to find B? By simply saying that if Tn represents any term, then T1 must represent the first term, 1 describing the first position in your pattern. So that would be 3 times 1 plus B, and that's equal to 5 in this case. So our B would be equal to 5 minus 3, which would equal 2. So we now say that for this unique pattern over here, that our Tn is 3n plus 2. And now, without doing any other calculations, what would T50 equal to? In other words, the 50th term in this pattern, what would it equal to? That would equal to 3 times 50 plus 2. So we've got 150 plus 2 is 152. Look how elegant that is, that without going and adding and adding and adding until you get to the 50th, we've actually established what the formula is for any term, and we've been able to say, using that formula, just quickly we can plug in any value that you'd like. So if we wanted to know what the 1000th term would be, we wouldn't have to sit and add threes for 1,000 times. We could just say 1,000 times 3, 3,000 plus 2, 3,002 is the value of the term. Okay, so let's give you a little bit of a challenge. Let's go up here and say Tn is equal to 301. And let's give you the sequence of, okay, let's just do this. Let's erase that. If Tn is equal to, and we've also got that the sequence is, let's make it 4, 7, 10. Okay. Now I know that you've picked up a little bit around how to get the nth term. My hint to you is to find out what Tn is first, and in the general term, and then I'm going to leave you to play a little bit. Tell me what you think the term is. What is n? What n gives you a term of 301? Okay, so if Tn is 301 and the sequence is 4, 7, 10, what is n that gives us 301. And over to Indy so she can take us through that.
Fantastic,
Challenge.
guys. Yeah, so what we're going to do is we're going to take a quick break. I'm one finger click away from actually posting the question. So that's what I'm going to do. Guys, have a little think. You've got about 2 minutes, and we'll see what the answers are when we get back. So, see you after the break. Welcome back, Mindsetters, and I hope that you're having a fantastic session. I see that lots of you are actually writing in and letting us know answers to the question. We're still waiting. Guys, let us know if you have the answer. Dina, they're taking a bit of time. I'm just hoping that Facebook's being slow. That's what I'm hoping. We do have a question in the meantime that we can go over.
Okay.
Okay.
Let's have a look at that.
So this one is from Megan, and Megan wants to know, can B also be negative?
Well, Megan, you're on your way to being a mathematician because that's the kind of questions that mathematicians ask. What if B is negative? Or can B equal be a negative? Did you think about A? Could A be negative? Okay, so if you really have understood a concept, you can really take that test of asking those fantastic questions. Can B be a negative? And the problem with mathematics often in class is that your teacher will do a beautiful example where everything is positive and everything works out nicely. All of a sudden you get given the homework, you arrive home, and all of a sudden it doesn't work like the teacher showed you in class, right? And you then need to be that mathematician in action and say, well, let me work through this and see what other permutations I can get out of this. And certainly let's have a look what other values B could come out as. And let's also, Megan, and for everybody else, see what A could also equal. So let's look at the sequence of -5. Let me pose one. -5, -7, and -9. Okay? And let's see what would Tn come out as. Okay? Well, firstly, let's look at what's happening between -5 and -7. So let's look at T2 minus T1. What do we get? We get a -7 minus a -5. So we get, in the end, a -2. And what's happening between T3 and T2 is the same. We've got -9 minus -7 is also -2. So before you jump in, and this is a good rule, just have a look, are we adding the same thing? So are we expecting it to be linear, or is the sequence doing something completely crazy? Okay, so we've established we were adding -2 to -5, and we were adding -2 to -7, so certainly it is linear. You only need to be given a minimum of 3 terms to establish that. So now, if T2 minus T1 is -2, what does that tell us? That if Tn is always An, so if Tn is always An plus B, that we now have a Tn of -2n plus B. So we start off with a formula with a plus B. You can use a minus B if you like. It doesn't really matter. It's irrelevant. But in the end, the B value that you get, let's go and investigate that, what it could be. So we're sitting now with a coefficient of negative. So remember the evens and the odds, they had the coefficient of 2. All of a sudden, A comes out negative. So yes, A can be a negative value. And then, are there any constraints on B? Well, how do we get to B? We take the first term, which in this case is -5. That's T1 is -2. Remember, n stands for the number in the sequence, so it's 1. And plus B, and this is now equal to -5. Okay, let's solve for B. We get a -2 over here, so the B is -5 plus 2, so B comes out as -3. So there we go. B can also be negative. So this Tn for this sequence is -2n minus 3. So that's our general pattern. Remember, n will always be to the power of 1. The coefficient in this case is negative. The constant in this case is negative. And in fact, some of you might be thinking, where am I getting these numbers from? Where are they coming from? I'm not making them up. I'm actually starting with -2 and -3. So I created my own coefficient and my own constant. And because you asked me if B was negative, I created a -3 to give me that sequence. And then we've worked backwards. So if you wanted to practice this on your own, it's a fantastic section because you can start off with the linear, Work out what your terms is and then try and work back to see if you actually get that general term. And you'll see how fulfilling that is if you can go from one to the other. But Megan, that's an excellent question, and my girl, you're on your way to being a great mathematician. Keep it up.
Fantastic. I know we've got about 1 minute to the break, guys. So what we're going to do is, guys, get those answers in, and we're going to answer the question after the break.
Great.
But Dina, what you were quickly talking about, Sean wants to know, what is the difference between a coefficient term and a constant term?
Excellent algebraic question of revision. Let me just get my page down. So let's just write those words down because they're very important to talk mathematically. And if you're on Facebook, you must use the right wording. So what is a coefficient? And what is a constant? Okay. I'm going to give you an example from what we've just done. We had Tn as minus 2n minus 3. So every expression will have some variables and then some numbers. And the position of those numbers is how we define those words. So a constant basically means that that term cannot change. In other words, it doesn't have a variable attached to it. The word variable has the root word vary. And that's why it's the expression varies, because that variable will change and so will the value of that term. But a term that doesn't have a variable attached to it will not change. Hence the word constant. Constant means it stays the same. So which one of these two would stay the same? Well, negative 2n won't stay the same because n can change. So therefore negative 3 would stay the same. So that's what we call a constant term. A constant term is that which doesn't change. A coefficient, there's no such thing as a coefficient term. The coefficient is just a word that stands on its own, and it is the value that comes adjacent to the variable. That position of that number is known as the coefficient. So it's not a term, it's just a place value.
Fantastic. There you go. Guys, we're going to go to a quick break. When we get back, we'll be answering that question. See you now. Hi guys, and welcome back. There are a few of you that have written in, and I can see a few correct answers in here, and so can Dina. But what Dina's going to do, she's going to go through it, and then afterwards we'll let you know if you got it right. So take it away, Dina.
Thanks, Indy. Right, I left you with the sequence 4, 7, 10, and I also said the nth term is 301, and the challenge was to find out which term gives you that value of 301. Now, you could have sat on the couch and literally have added up in threes, because we can see it goes up in threes. But remember, you want to be an efficient mathematician, so you really want the quickest way to the answer. So let's see how you would go about that. Right, so Tn we learned today is linear, an plus b. How do you know that? How do you know that it's linear? Because we've added 3 to 4 to get 7. We've added 3 to 7 to get 10. So since we've added the same amount, it's linear. What happens if we, just to divert a little bit, if we looked at the sequence 1, 1, 3, 2, 3, 5. This sequence is made up by adding the two terms before it. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5. So we're adding that. That's called a recursive sequence. And that is a very famous Fibonacci sequence. Your teachers might have posters about Fibonacci on their walls. So go and have a look at that. Very, very famous sequence. Right, so an example of where you're not adding the same thing every time. But in a linear, you certainly are. And then the next thing we'd like to do is find out what is that A. And it's always the second minus the first, which in this case is 3. So 7 minus 4 is 3. So we had a Tn of 3n plus b. So the coefficient is 3. There's no such thing as coefficient term, just the coefficient is 3. And what was the constant? How do we do that? Grade 10s and everybody else, it doesn't matter what n is. We could have taken 7 or 10 as the second and the third, but the first one's the easiest one to work with. It's the smallest one. So T1 in this case was 3n plus b, and that was equal to, let's just get this in, that n is 1. Remember, if you've chosen 1 as the first position, then you want to use the same n value. The n in both cases is the same. It doesn't change. And this is equal to our first term, which was 4. So what is b equal to? b is 4 minus 3, which in this case is equal to 1. So firstly, the Tn was equal to we've got here a 3n plus 1. 3n plus 1. So now we know that the value of some term in that pattern is 301. What is n? So you had a little equation to solve here. Minus 1 from 301 would be 300. And then you'd be left with 3n was equal to 301, and therefore making n the 100th term. So for those who got the 100th term, and you got the sequences 3n plus 1, have actually really grasped the section, and you're well on your way to scoring full marks for your number sequences in your exam. Well done, everybody. Were there any of those that got that answer?
They were. Well done, mindsetters. You did really well. I know Steph got the right answer. Sizwe, you got the right answer. Santaga, Lisa. So well done, guys. And thanks so much for participating and sending in those questions. I think it's really, really cool and quite fun. Okay, so we've got one more question, guys, and we've got 3 minutes left. Can you believe that time has flown? I can't believe it, Dina. So let's try and get to this one. Let me just have a look. Now, this one was sent in by Sizwe, and Sizwe actually put it onto the page, and he actually sent it to the grade 10 mindsetters, but no one's answered, so I feel very sorry for him. So I said, we'll answer it for him. So this is what Sizwe had to say. Let me see if all the grade 10s are listening directly to mindsetters. What is the difference between linear and quadratic equation? Shake your minds up, grade 10s, smile. So, guys, no one wrote back to him. It's okay, Sizwe, because we've got you. Dina?
Sizwe, it's wonderful. Don't you want to come and be a teacher too? Because you're already posing the teacher question. So that's wonderful to see how you're interacting. It's great. Keep it up. Difference between linear and quadratic, we did mention earlier. And we mentioned that an expression is labeled by its highest power. So if we just do a little table of values and look at what the linear really represents, a linear is an expression where the highest power of the unknown is 1. So that makes it a line, a straight line. The quadratic is a little bit more strange to English speaking folk, because whereas line really represents the highest power as 1, the word quadratic, there's no English word that represents that, but it comes from a Latin. It comes from the Latin root word quadrado, which means a square. So therefore, those that have got Latin background would understand that a lot better. And so quadratic would be let's just go a n squared plus b n plus c. And then we'd build it up and we'd go on to a cubic being a n cubed plus b n squared plus c n plus d. So you'll see that when we build it onto a square, that the square still has the linear and the constant, and the cubic still has the square and the linear and the constant, but the highest power defines the name of that expression. So power of 1 is the highest, here the power of 2 is the highest, here the power of 3 is the highest. And next year we'll deal with patterns that have got power of 2 as its highest power, and therefore it's got a coefficient that you'll also be able to find out. It's not found out in the same way as we did with the linear, but we'll discuss that at a later stage. So, Sizwe, that's the difference between quadratic and linear. Anything else?
I think that's it for now, guys. I can't believe it, but we've actually come to the end of our session. I don't have it on me now, but guys, we are giving away a Casio calculator, and there have been a lot of you that have actually been, you know what, Sizwe, my friend, please, I'm going to send you a message on Facebook. You've won the Casio calculator, and you're going to send us your postal ID, and we're going to send that to you. Guys, grade 10s, Anele, I know you're watching. You're on next. Grade 10s, I know it's come to the end. We had a fantastic show. Thank you and goodbye.